So for the purposes of the video, hello, I'm David, in case you've never seen me before. That will do. So this is a written seminar for Intro Math Econ Advanced. It's 2015 in semester 2, those of you who are watching this in the future. I've been asked at the moment to talk about integration, which I will do. Now, I'm not 100% sure of the sorts of things that are covered in your course. I was sent a list of some lecture notes, but that's not the same as knowing the sorts of questions that the lecturer expects you to be able to do. So there are some things about the limit definition of integration that I'm not sure. So did you have to do any where you had a sum and you had to show that it came out to an integral, or was it all, here's an integral, what's the answer? Here's an integral, that's the answer? Sweet. Very nice. Okay. All right. I will just do a bit of philosophy. So integration was originally invented and still is mostly about areas. And it tells you about, when it was first invented, it was about the area under a curve. So you have something like that. That's like y equals f of x. And then you have the area under that curve between 2 points. And what you'll say is this area is the integral from a to b of f of x dx. And that's what that means. Okay, so definite integrals were invented first, before definite integrals. And so this is called a definite integral. And it literally describes the area between here and here, with a little bit of extra care, because if the area dips below the x-axis, it counts as a negative area. So if you have something like this, then this area is negative, and this area is positive, and this area is positive. So if you did the integral from say here to here, the answer would come out as a negative number because that bit's below the x-axis. So that's just an important thing to know about areas. If it's below the x-axis, it's negative. Okay. And the other thing about area is what people use it for in a lot of practice is the average value of a function. So you can say, well, if I've got like y equals x squared between 3 and 5, on average, what is the value of that function? And so a function that's strongly sloped, that goes up really fast, the average will be higher than one that goes up slower, because averages are pulled towards the higher numbers. And so the way that you can figure out an average is to divide the area by the width, and that will be the average value. I don't know if that's in your course, but it's useful to know for the theory of how integration is done. So, right. So this thing here, similar to with derivatives, the dx represents a very small change in x, and the fx represents a height. And so what you're actually doing when you're calculating an area is that if you zoom in very close on a very tiny sliver, you're saying, well, this is dx wide. Some people call it delta x. And it's f of x high, because that's what the function value does. And so the area of this slice is f of x times delta x, because it's f(x) high and delta x wide. So lots of little tiny rectangle slices, and then you add them all up, and you get dark enough to see, and total area is the sum of all of the f of x delta x's, and that's a capital sigma for sum. And then the thing is that if you have infinitely many of these little tiny slices, the delta x becomes a dx because it's so small that you can't see it. Same as with derivatives, a change in x becomes a d because the delta is the Greek d and the d is the English d or the French d because that was invented in France. And so delta x becomes a smooth like that. So this, the capital sigma is the Greek sound for sum, and then when it, you make these smaller, and it goes from being something that's a little bit pixelated to something that's smooth. So this is a smooth S shape, and this is a kinky S. So that's the philosophy behind it. It's not very important, but it helps me know what's going on. Okay, and then Newton, and mainly Newton, discovered the fundamental theorem of calculus, which said that, hey, it's not just areas. The integrals totally are areas, yes they are, but the way to find integrals is to do differentiation backwards. And until that point, no one realized that derivatives and integrals were related to each other. Derivatives were finding slopes and integrals were finding areas, and suddenly they realized that you could find an area by doing differentiation backwards. And the world became much easier. So there we go. So also can do integration by differentiation backwards. And that's called the fundamental theorem of calculus. Yeah, that's the fundamental theorem of calculus. It's one of the coolest things ever. And it's remarkable that they should be related at all, actually. There's no particular reason you would expect that slopes should be related to areas. But they are. So there you go. Good. So that's just prelude. So when you're actually asked to do an integral, there are two different approaches depending on whether you want an area or whether you want to just undo differentiation, because one can undo the other. So there are two different things. So you have a definite integral, which says that if you want to do this, then you do this, where capital F is something that differentiates to give little f. So there's that. And what that means is this is shorthand for subbing in B and subbing in A and subtracting. That's a definite integral. So to do a definite integral, you happen to think of something that differentiates to give this answer, and then you sub in the top end and the bottom end, and it magically comes out to the area. And you don't have to, there's no particular rule as to which thing that differentiates to give this answer. You need to pick. Any of them will do. And because any extra plus c's and extra constants will cancel out when you do this subtraction. And an indefinite integral doesn't have the numbers attached to it, and it's just something that differentiates to give that answer with a big plus c, to point out that if there was an extra constant, if I differentiated it, it would disappear, and then they would all differentiate to give this answer. So if I knew that this was x squared, well then x squared plus 1, when I differentiate it, would still give 2x. No, so you need the big plus c or d or whatever constant you like to indicate that there are many different possible things that differentiate to give this answer. So the goal of this one is to find an area, which means the answer is a number. And the goal of this one is to undifferentiate, or some people call it anti-differentiate. And the answer is a function. Okay, so the answer is a function formula. This one, the goal is an area, and the answer is a number. So that's the idea behind it. Yay! Okay. So integrating requires several different skills, and it's harder than differentiating because it's harder to recognise what to do. Excuse me. So differentiating. Oh, good. I am recording. Differentiating has about 4 different basic. Well, some of them are less basic than others, but 4 different rules, and they always work. And if you use the wrong one, it'll still come out to the right answer anyway. So you could do some things with the quotient rule and some things with the chain rule, and it still comes out fine. With integration, it's harder. And so there's a couple of techniques which can help you to integrate things without knowing in advance what the answer is. But the first one is to just do it, because you happen to know how to do the integral straight up. And so I have a list in my head of the things that you should try to do integrals, and it has about 8 things on it, but you learn 3 or 4 of them in this course. So this is my list of things to do with integrals. So my integral techniques. So technique 0 is just do it. Doesn't really count as a technique, you just have the answer already because you know what it is. And technique 1 is rewrite it first. And technique 2 is substitution. And technique 3 is integration by parts. And the reason I put them in this order is that that's the order of easiness. Okay? By parts is not that hard, but it's harder to see what to do, and it takes longer than substitution. So I put them in this order, and if I wasn't given a specific technique that I have to use, I would run through these and try all of them in my head before I committed to one of them, and I would start at the top. Okay, so to just do it, I do have to check some things. Did you do integrals and derivatives of trigonometric functions, like sine and cos? Okay, cool. I will not use them as examples. So just do it has sort of 3 different subcategories. One is just to know recognize the derivatives of things. You did do exponentials? Logs? Okay, good. And in this course, is it ln or is it log? Good. Checking. So there are some you're just supposed to know. So one is that if you have x to a power, then when you integrate it, actually I'm just going to change the way I draw this. In my head, integration is up and differentiation is down. And so when I remember all of these things, I arrange them with the integral above the thing that I'm integrating. That's just how I think about it. And the reason integration is up is because the powers go up when you integrate. So if I was going to integrate something, the power goes up by 1 and I divide by the new power. So that's the most basic rule. Power goes up by 1 and I divide by the new power, which is the opposite of differentiation. In differentiation, you times by the current power and then you put the power down by 1. So this one, it's not just the opposite things, but in the opposite order. So in differentiation, you times by the power first and then you put it down, and in integration, you put the power up by 1 and then you divide by the new power. Okay? And the only exception to that is 1 over x, so x to the minus 1. Because if you put the power up by 1, it'll get 0, and you can't divide by 0, and that one goes up to ln x. Some people, like over in Maths 1a, actually define ln x to be the integral of 1 over x. They don't define it as the inverse of e to the x, they define it as the integral of 1 over x. So, yeah. And then the integral of e to the x is e to the x again. So they're your 3 classic integrals that you should be able to do. Alright. And on top of that, there's a few rules. If you multiply by something, then you multiply the integral by the same thing. That's when it's a constant. So you see it written in your book like this. So these are the classic, and these are the rules. Those the rules say if you multiply by a constant, then the constant is still there after you integrate. So the way that the rule would normally be written would be something like this. I believe your lecturer used the letter lambda in that spot. Yeah, I am recording it. But I see that as... you're welcome. Constant multiplied is still there. So if the constant's multiplied, it will still be there after you integrate. That's what I have. And there's this one. So the integral of f of x plus g of x dx is the integral of f of x dx plus the integral of g of x dx. So that's saying that you can do each term separately. Things separated by pluses or minuses can be done separately. So they're the basic rules. Pretty sure there's nothing else very important at this stage for the just do it. And I'm just going to do a couple of examples, or at least one. So random crazy function, not that you would ever see such crap. You would in an exam, but in life. Just to prove to ourselves that we know what to do, the pluses mean that we can do each bit separately. It'll work with a minus as well. I could make that a minus. And those constants there allow us to just leave the constant there. So 3 is a constant that's multiplied on, so it will still be there afterwards. Multiplied on. X squared, well, that will go up to x cubed, and I'll divide by the new power. The 2 is a constant multiplied on. It's 2 times 1 over x, and the 1 over x becomes ln x. The minus 5 is a constant multiplied on, and the e to the x becomes e to the x. And because it's an indefinite integral, it doesn't have numbers, I'll put a plus c on the end. So 3 times a third is not there. E to the x plus c. Yay! And that's basically it, really, for doing those things. And there's, just as another example, there's 2 particular functions that do fit your power rule, but are probably worth remembering all on their own. So the 4 is multiplied on, so it's still there. The 5 will go up to a 6, and I'll divide by the new power. The 2 is multiplied on, but it's still there. Now x is actually to the power of 1, so the power will go up to 2, and I'll divide by the new power. And the 8 is multiplied on, and well, basically, if you see a constant by itself, it becomes 8x, or u, or whatever it is that you're integrating with respect to. Constants have an x attached to them. And it's technically because it's x to the 0, so the 0 goes up by 1. X to the 0 is 1. So 8 is really 8 times 1, which is really 8 times x to the 0. The 0 will go up to 1, and I'll divide by the new power. But it is worth adding it to your list of things to do. The constant will integrate to give constant times x, which is what I've used here. The 8 becomes 8x. Yep.
2x, how does that integrate to 2x times?
That's the times sign. That's why I write my x's like this, so that I can tell them from times signs. That's why most mathematicians actually do multiplication as a dot, but I have trouble doing that. So 4/6 is the same as 2/3. 2 cancels with the 2, like that. All right, there is one more thing on the just do it category, which is worth mentioning, because it is technically substitution, which we'll get to in just a minute, but most people doing maths expect you to be able to do it without mentioning substitution. You just sort of just go for it. So the last sort of, there's this other rule, and I say it like this: if the derivative of the thing on the inside is a constant, then you can just divide by the constant. That's how I say it. So derivative of the inside is a constant, then divide by the constant. And what it means, just as another thing, so that if you know that the integral of f of x dx is capital F of x plus c, then the integral of f of ax plus b dx is f of ax plus b divided by a. So if you would know what to do if the inside was just x, but it's not x, it's ax plus b, well, pretend it is x and divide by the a. It's particularly important for things like this. Like that. So if that was just an x, if it was just x to the power of the 5, I would totally know what to do. I'd put the power up by 1 and I'd divide by the new power. And since the thing on the inside, the derivative of that is a constant, I'm allowed to just go put the power up, divide by the new power. Great. And it's not x, it's 2x plus 3, so I can divide by the 2. And you're allowed to just, well, I think you're allowed to just do it. And there's another example. This one's very, very common where I come from. Like that. I would know what to do if that was just an x. It would just be e to the x. But it's not an x, it's a 3x, so I'll have to divide by the 3. And yeah, as far as I'm aware, you're just allowed to just go for it and do that. It's technically substitution, but I put it under the just do it category because it happens so often to see an e to the something x that you can just do it. You okay with that?
Oh yeah, I was curious about how that's substitution as well. I suppose we'll get to that once we get to substitution.
So, well, you could achieve the same result by substitution, and it would get there. Okay. All right, the next rule, the next technique is rewrite it. And some people don't think this deserves a technique of its own, but it's very useful to realise that it's something that you can do. See, that looks horrifying. And if it was differentiation, I would use the quotient rule. But there is no quotient rule for integration. But there is rewriting it. Look, I can divide, division expands out over addition, so I could just go like this. That's x to the minus 2, that's 1 over x. And I can integrate both of those. Power goes up by 1 to minus 1, and I divide by the new power, and that goes to ln x. Magic. Okay, so the first thing you should check with anything is to see if a little bit of algebra would turn it into something that you know. You don't have to try substitution or anything fancy. Just see if you can do a bit of algebra. Okay? So I don't really have any other examples at this time, but it is worth just pointing out that that's something that you can do. You can always rewrite it. Just as another classic would be something like you'd look at that and you'd go, oh, it's two things multiplied together. I'm supposed to use integration by parts or something like that. And say, no, don't do that. Just expand it out. And now I can do each bit separately. Great. And I know that sounds bad, but there are so many times in an exam where you would forget and do something really hard when actually it was something easy. So keeping it as a thing in your mind, say, can I just rewrite it to make it easier? It's a useful thing to do. So that would go up to 4, I divide by the new power. That would go up to 3, I divide by the new power. So that's the deal. Right. Good. That's as much as I'm going to say about that, but it's worth pointing out because it's like a double bluff, some of these things. Okay, substitution is a particular method of integration. Technically what you're doing is you're remarking your x-axis according to a different scale. And so if you do that, if you remark your x-axis according to a different scale, then it may be easier to calculate the area. So suppose you remark your x-axis according to x squared instead of x, then let me show you. So this is the philosophy. So currently it's marked according to x. If you wanted to remark it with u equals, say, x squared, not x squared, u equals, say, root x, then this could be remarked as 0, 1, that would be root 2, this would be 2, this would be 3, and that would be my u there. The 9 would become 3, the 4 would become 2. Okay? So I could say, well, I'm going to have my u-axis is going to match up with my x the way that u is root x. And so my graph up here, like that, or like whatever it looks like, is going to look different according to this axis, because this zone from 2 to 3 is wider than this zone from 1 to 2. So what I'll do is I'll shrink it all back down so that it all lines up properly, and that will change the shape of my graph and therefore make it easier to calculate the area. So there are some things that if I had something like, say, this, like that, well, if I shrunk this bit in and that bit in, it would actually become a straight line, and that's easier to find the area of a straight line because you can just use triangles and rectangles and stuff. That's the philosophy behind it. And the problem is, though, that widths here, that delta x, that dx, is actually, when I remark my u-axis, that dx there, if I actually shrink this down to the size it's supposed to be, it's like teeny tiny. That's my du. Because this thing here is the same size as that, sure, but when I shrink this down to be the correct scale, so that this distance here is the same as this distance here, my width here becomes even smaller. Whereas this width here, which is the same distance as a dx, doesn't become quite as small. No, I'll put it in a different spot. This width here doesn't become quite as small as the other one. So my du, depending on where I am in my u's, is a different size relative to the dx. And so I need to find some way of adjusting my widths so that they're the right width. If that confuses you, feel free to ignore it, but that's what's going on. You're remarking your x-axis according to a different scale. So, here's the idea behind it. Not the idea, here is how you do it. And I can't describe it generally, it will only work if I do an example. So let me do the example I did before, like doing substitution. So I'm going to go that this is the thing that you think in your head. In substitution, you see something that is inside another function. So it's for functions inside functions. I'll just put that up here for functions inside other functions. So, which is a chain system we would use the chain rule for if you were doing differentiation. So the substitution is the chain rule, but for integration. So you look and see, oh, if that was just an x, I would know what to do. That's my mantra. If that was just an x, I would know what to do. And so I can pretend that I can replace it with something else. I can say let u be equal to 3x. And that will replace my 3x with a u. And then what I'll do is I'll replace my dx with something in terms of du. Now here's my problem. I didn't actually see a specific example of how to do substitution in your notes. Did I just miss it? I'll just look that up. Just give me a second. Sorry? Oh, is that a new one from that you just sent me?
I sent you one in the comments.
Okay. That's why I was a bit confused. Come on. Are you going to open?
Encouraging my substitutions at the bottom.
Yeah, it's not really a description.
The lecture notes confuse me.
All right, cool. No, that's good. I can do it from here. So I want to know how big the du is relative to the dx. So when I remark this axis, see the du, it's all stretched out here, but when I put it down so that everything is the same width, some du's are bigger than other du's. And this du is like half the size of that dx, but this du is roughly the same size as that dx. So it depends on which x or u you're up to as to how big the du is relative to the dx. And we already know how to figure out how big a du is relative to a dx. That's du on dx. That's what that is. It's the derivative. So I'll figure out what du on dx is. And it's 3. And that tells me that du is 3 at times the size of dx. Is that all right? Now here's the thing, my philosophy of doing substitution is that I go looking in my integral for the things that I have here. My 3x is u. I don't have a 3 dx in my integral. I've just got a dx. So if I divide both sides by 3, now I've got what dx is equal to. This dx is here, I can replace the dx with a third of du. And so I get, therefore, the integral of e to 3x dx is actually, the e is still an e, the 3x is a u, the dx is a third of du. And so let's see, the third is multiplied on, so it will still be there afterwards, and the integral of e to the u is e to the u. But e to the u is really 3x, so I can put it back in. And it becomes a third of e to the 3x, exactly as it did before. So last time I just did that by dividing by the 3. But substitution proves that it's true as well. Okay, and the reason you divide by the 3 is this move back here where I had to move the 3 over this side. That's why the 3 became divided. Okay, so that's substitution. But you don't need to use substitution for that particular example because you can just divide by the 3 as you go because you're allowed to just do that. But sometimes you do need it. Let's do something really huge. If that was x, 2x plus 1 squared, I would have just expanded everything out. Okay? So if I saw this, I wouldn't have used substitution. I mean, I've noticed that there's something inside another function, but I would have just expanded that out, right? So, you know, don't do substitution. Just expand it out, you know. You've got 4x squared plus 2 times 4x plus 1. And then I can just do my power up by 1, divide by new power, power up by 1, divide by new power, power up by 1, divide by new power, and there it is. So I don't need substitution if the power is low enough for me to be able to expand it out. Okay? Don't need to do substitution. The reason I put it in this section is because I want to point out that even if you think it's substitution, you should go through your other list and say, could I rewrite it? Because that's easier. Possibly not. It might actually be quicker to use substitution, but I'll do it by substitution as well with a different number. Okay, so what if I was going to do, what if it was like this? I'm not going to expand that out. That would take me forever. So now is when I start to go, yeah, expanding it out doesn't sound like fun. I've noticed that there is something inside another function that I would know what to do. If this was, if that was just u, I might have the slightest chance of knowing what to do. This x here is a bit annoying, but we'll deal with that later. So let's give it a try. Let's call u equal 2x plus 1. Then du, I need to figure out how big du is relative to dx. That's always the first step. So du is 2 lots of dx. And actually, I don't have a 2 dx, so I will do that. So I'll put the dx up there and divide both sides by 2 and I get this. So now the good thing is I can deal with the dx. I've done that. I can deal with the 2x plus 1. I've done that. There's still an x left over though, which is a problem because this has turned into a du, this has turned into a u. There's still an x. Everything has to become a u. And so what I'm going to do is I'm going to go back to my beginning, just here, and rearrange it to figure out what x is in terms of u. So u minus 1 equals 2x, and so a half of u minus a half is equal to x. And so that's what I'll do. So each piece of my integral has become something in terms of u. The x is just here. The 2x plus 1 is u. And the dx is a half du. Now that looks still complicated, but now let's ignore and let's pretend that we didn't know where this came from. And we looked at that and we go back to the beginning and say, well, can I just do it? Well, no, I can't. Can I rewrite it? Yeah, I could totally expand that out. That would turn into something that I could do. So let's see, a half of u times a half of u to the 52 would be a quarter of u to the 53, and a quarter of u to the 52. And what I've done is I've expanded that out. And then I can just integrate it. A quarter of u to the 54 and divide by the new power. U to the 53 and divide by the new power. Like that. And then, oh gosh, I don't know what 4 times 54 is, 216. But just a second, it was originally in terms of x, so I need to put my u's back. X back, u is equal to 2x plus 1. So I did several things in that line. I figured out my fractions, that's how I got these numbers. And then I replaced the u with what it really is, which is 2x plus 1. So let's just see if we can pull apart what happened there. I chose my u first. That's what I did first. And then from that I figured out my du, my dx in terms of du. Then I went back and I dealt with the last x. That's what I was looking for there. And then I subbed everything in, which is what I did here. And then I expanded it out, which is what allowed me to integrate it. And then, so then I integrated it. And then I put the u's back, the x's back. So this one was replacing x with u. This one was doing the integral, was expanded out, which may or may not be necessary. This one was the integral, and this was replacing u with x. So you start by replacing x with u, and at the end you replace u with x. That's an important thing to finish off with. So one more example. That was actually quite a complex example, that one, because it had something that you don't often see. And I will do one more after that as a definite integral. So let's look at this one. Can I rewrite that? That doesn't look likely. We've got a mixture of x squareds and of powers of x and e to the power of stuff, so that doesn't look likely. So my next step is to look inside another function and see, oh, just a second, I've got something inside the e to the power of. I'm going to give it a go and say, let's let u be the thing that's inside the other function. Like that. Alright, so that deals with that bit there. We're good with that. Pretty much always deal with the dx next. So I need to figure out how big du is relative to dx. The 5 is multiplied on, so it'll still be there. Then it's 3x squared. The 1 will disappear. I'm differentiating here, so the powers are coming down rather than going up. So that's 15x squared. So I've got that du is 15x squared dx. Now, here's something that I do when I do substitution. I don't know if your lecturer does it that way, but this is how I do it. I look to see if I can include as much as I possibly can with the dx up here. So I've got this, that's u, and I've got a dx and an x squared. If I could join that x squared with the dx and turn it into a du, the x squared would disappear. So come down here. I do have an x squared joined to the dx here, and that's what I've got here. The x squared and the dx joined together. But there's a 15 in the way. I really prefer that to be a 3, because that's what this is here. So I would, to make this match what's left, I will turn that into a 3. So if I divide by 15 and times by 3, now everything matches. The 3x squared and the dx together become 3/15 of du, which is the same as a fifth. Like that. So these two bits here, that bit together with that bit becomes 1/5 of du. And so I can do it. I've got 3x squared e to the 5x cubed plus 1 du is those two together is 1/5 of du, and the e is still e, and the 5x cubed plus 1 is u. And now I'll ignore everything else and just integrate that as I always would. A fifth is still there because it's multiplied on. The integral of e to the u is e to the u, and there's a plus c. But the u is really e to the 5x cubed plus 1. And that's how substitution works. The only other thing that will happen in substitution is that the limits might change, and you might have a definite integral. What if it's a definite integral? So what if I do that same one, but with a definite integral? From 0 to 2, say. Well, in that case, I'll still do everything that I used to do. I'll still go u equals 5x cubed plus 1 because that's the bit on the inside. And I'll still figure out what du on dx is. And I'll still rearrange that so that I can get everything to match. Okay, and so now that and that together I've figured out. But the thing is that this 0 technically is x equals 0. And this 2 here technically is x equals 2. So what I'm going to do is I'm going to say, well, if x equals 0, what does that mean about what u is equal to? X equals 0 means that u would be equal to 5 times 0 cubed plus 1, which is 1. And if x is equal to 2, that means that u is equal to 5 times 2 cubed plus 1. 2 cubed is 8, 5, which is 41. So I can go back and imagine and remind myself that this is actually x equals 0, this is x equals 2. And so the x equalses will need to be turned into u equalses. And that's coming from this formula here. By the way, that's how I'm figuring that out. And so each part of my integral is going to be replaced with something involving u. The x equals 0 is replaced with u equals 1. The x equals 2 is replaced with u equals 41. Now you don't have to put the u equals, but I find it really helpful to remind myself that I've dealt with everything. The 3x squared dx became a 1/5 of du, and the e is still an e, and the 5x cubed plus 1 is a u. And so what I'll do is, because it's a definite integral, it will go from 1 to 41. So I've got the fifth is still there, and e to the u becomes e to the u. And so that's equal to 1/5 of e to the 41 minus 1/5 of e to the 1, which is whatever it is. It's not a pretty number. It's a very, very large number, I would say. So I have taken this number, this thing here, and I've put in the u equals 41, which is there. Just for my own things, that's my u equals 41, and that's my u equals 1. And I've subtracted the two of them to get the answer. And it's a number, it's just a really big number. I don't like it. Yeah, e to the 41 is going to be like wickedly huge. So how do you feel about that?
Yeah.
That's all right. I'll keep going. Even if you both leave, I'll keep going. Okay, so that's substitution. So you'll notice that there are a few tricks with the substitution. The important part is to figure out what's on the inside. Sometimes the inside is the bottom of a fraction. So I will do one more. that one there. Let's do it from one place to another. Let's do it from 0 to 1, or maybe to 3. Okay. So the first thing we would do is we would check to see if we could divide to figure out what this was. So because the plus is on the bottom, I can't just do a division and expand it out. If it was x squared plus 1 on x, then I just divide them both by x and I could do ordinary integration. I could just rewrite it. So, but because the plus is on the bottom, I'm stuffed. The next thing is to try and do substitution. The most annoying bit here is the fact that the x squared plus 1 is on the bottom. So if I called that u, it would be inside another function, which would be 1 over that function there. So I will call that u. And that will deal with that bit there. That's u. So the next bit is to deal with the dx. You always deal with the dx next. Du on dx would be 2x. And then I've got du equals 2x dx. And then I can go looking here and go, now let's see. Dx is, I don't have a dx all by itself, but I do have an x here that I can join with that dx just like it is here. Because this is really, if I thought of this as a number, it would be x dx on the top of that fraction. So I can join that x with this dx. Which is great. So I do have an x dx, and I can, therefore I should move that 2 away and divide by 2 to get a half of du. So I've dealt with the x dx. The x dx is a half of du. That leaves me for dealing with the x equals 0 and the x equals 3. So when x equals 0, that means that u is, according to this formula, 0 squared plus 1, which is 1. And when x equals 3, that means that u is equal to 3 squared plus 1, which is 10. 3 squared is 9, and plus 1 is 10, yep. So, just so that you can see what's going on here, I can imagine this like this. That's what I'm seeing there. I'm moving the x off the top of that fraction to join with the dx, so which will leave behind a 1. And so let's see. My x equals 0 becomes a u equals 1. My x equals 3 becomes a u equals 10. My 1 over is still a 1 over. My x squared plus 1 is actually u. And my x dx is a half of du. And so now everything involving x has been replaced with something involving u. And let's see. The half is multiplied on, so it will still be there. 1 over u will become ln u. And it's going from 1 to 10. And so I'm going to get a half of ln 10 subbing in the 10. And a half of ln 1 subbing in the 1. And I'll subtract the 2 answers. But interestingly, ln1 is 0, so I can make it slightly simpler. Yay! Okay, that's substitution. So, key is to find that most annoying bit that's inside something else, and then to make sure that, and deal with the dx, and then make sure that everything that involves x is turned into something involving u instead. And the last technique that's in your course is integration by parts. So integration by parts is the product rule for integration. So with substitution we have, not substitution, with differentiation we have the chain rule, which becomes substitution when you're doing integration. And with differentiation, we have the product rule, which becomes integration by parts when you're doing integration. So it's like the product rule. Yeah, sort of the product rule for integration. It's designed to deal with things that are multiplied together. But it's very important to realise that sometimes things are multiplied together when it's substitution. So you should always check to see if it's substitution first. The substitution is usually slightly easier than integration by parts. And when I say easier, just less places to lose a minus sign. So we all know how difficult it is when minus signs sort of appear and disappear at random, because it happens to us all the time. And so integration by parts has more scope to lose minus signs, and so I would prefer to do substitution over integration by parts just because of that. My knowledge in myself of losing minus signs at random. Sharpening my pencil here. Right. So I remember it took me years to remember integration by parts. I used to derive it from the product rule every time, and I was wasting all this time. And so what I do is this: I know that it has two. Your lecturer uses U and V, I think. So I will do the same. There's three UVs. It's all about the product. It's all about things that are multiplied by each other. And you see a U and a V in your integral. And what you're going to turn it into is something that doesn't have an integral sign, so the integral's already been done, and something that still has an integral in it. So what the integration by parts does is it doesn't do your integral for you, it just does part of your integral and it leaves you with another integral still to do. So it really turns your integral into a new integral that hopefully you know how to do, which is the same as substitution. Substitution doesn't do your integral for you, it just turns it into a new integral that hopefully you know how to do. Now this is not quite finished yet, there is something missing. The way that integration by parts works is that you look at what your integral is, and you look at these two things that are multiplied together, and you imagine that one of them is already the derivative of something else. So you imagine that one of these is already the derivative of something else. So say that one, for example, and then over this side, it'll be the other one that's the derivative. So it could just as easily be this. The dash could be on the U and the V on the other side. As long as one of them has a dash on one side and the other one has a dash on the other side, it'll work. So I never remember which one is which, because I just go, well, it's a U and a V and one of them has a dash and the other one doesn't, and it doesn't matter which one as long as they swap over. And it's just worth pointing out that if you have it as a definite integral, this one here that's all by itself is the result of integrating, so it will actually be like that. And one will have a dash here and the other one will have a dash there. So it's just worth pointing out that there's a definite integral version of integration by parts. Yeah. So if these two have numbers, this one has to have numbers too. And when you have a plain function with numbers, it just turns like that. It's the result of doing an integral. So this is what you get after having done an integral, so that's what you get after having done a definite integral. So that's integration by parts. And the key choice you have to make is which one of them gets the dash. So whichever one has the dash here won't have a dash later, so it will become integrated. So what will happen is that you'll get that the U dash will be integrated and it will become a U, and the V will get differentiated and it will become V dash. That's what's going to happen during this process. So therefore, whichever one has the dash, you need to know how to integrate it already. So if you don't know how to integrate it yet, then you can't choose it to be the one with the dash. Okay, so let me do an example. The first thing I would do is check to see if I can rewrite it. Nope, I can't expand it out. That's as good as it's going to get. All right, so that's the best I can do. The next thing I would do is see if substitution would help. Let's see, well, what's inside something else? This x is inside an e, but if I just called that u, everything would just become u, and it would be the same. It would be u e to the u be u, and I still don't know how to do it, so substitution is not going to help either. But it's worth checking first. Okay, so if it was this, I'll rub that out in a second. If it was this, u equals x squared, du on dx would be 2x, which is nearly this, and so I should be able to do that one by substitution if it was an x squared. And so I will be perfectly fine if it was an x squared. But it's not, it's just an x. So I'm going to have to use integration by parts. And how I set it out is like this. I'm going to leave some space. Okay. I've left a gap here so I can tell the reader what u and what v stand for. And I know that on the next line, this is going to become uv minus uv dx. But one of them will have a dash and the other one won't. So that's the thing I need to decide. So I'm going to have u equals and u dashed equals, v equals and v dashed equals. That's what I'm going to fill in now. I'm going to tell the reader. I could probably even put a let. Okay, you don't need to put those lets and ands in. I just think it looks prettier. So, okay, I'm going to need to decide. So if this is the one that had the dash, if the x was the one with the dash, when I differentiate it at the other end, it'll become a 1, and 1 is totally better, right? I don't have to worry about a 1 times stuff. And let's just try it again. If this was the one without the dash, if this was the one without the dash, it would become differentiated. If it was the one with the dash, it would become differentiated and it would become an x squared, and that's going to be worse. Like higher powers are generally harder to integrate. So the best choice would be to have this one have the dash, like that. So if the u, because if the u was here, it gets differentiated, x gets differentiated, it becomes a 1, that's going to be way easier. So it's almost always best to integrate an e to the x, because an e to the x is easier to integrate than a function, because it doesn't do anything when you integrate it, it stays the same. So therefore, let's line everything up. U is equal to x, and v dashed is equal to e to the x. So I've filled them out. So let's see. If u is x, then u dashed will be 1. If v dashed is e to the x, it'll integrate to give e to the x. So this one differentiated, and this one integrated. Just so you know what happened there. Doing well, and now I sub everything in. So let's see. U is equal to x, v is equal to e to the x, u dashed is 1, v is still e to the x. And I've now created an integral that I know how to do. I know how to integrate 1 times e to the x, because 1 times e to the x is just the same as e to the x, and the integral of e to the x is still e to the x. That's integration by parts. I'll do another one. Let me do a definite integral. No, I won't go to e squared. That's a bad choice. Let's do that one. Well, I could try substitution. I could go u equals ln x. And actually, surprisingly, that would probably work. Because it would go... but it doesn't look fun, because I would have to convert all my x's into e to this. No, not going to do that. So substitution doesn't look like a good idea. So integration by parts is the go. And integration by parts is specifically designed for products, so it's a good idea. So I'm going to do it again. I'm going to leave myself some space to say that u equals and u dashed equals and v equals and v dashed equals. Okay. And I'm going to turn this into u and v. And then when I integrate it, it will become uv minus the integral of uv. But because it's a definite integral, everything's definite integrals. And now all that needs to be decided is which one's going to have the dash. Okay, well, ln x. I don't know how to integrate ln x, not off the top of my head. So it can't be the one with dash, because if it was, I'd have to integrate it. So the dash is going to have to go here. Yep, if ln x was v dashed, I'd have to integrate it, and I don't know how. So that's what I'm going to do. So let's have a look at what I've written here. The u dashed is equal to x squared, and the v is equal to ln x. When I'm going to have to integrate the u dash to become a third of x cubed, and I'm going to have to differentiate the v to get 1 over x. And now I can go looking and sub everything in. Okay, so that's integrated to become a third of x cubed, 1 over x. So u is a third of x cubed, and v is ln x, from 1 to 3. U is still a third of x cubed, and v dashed is 1 over x. Okay, so a third of x cubed ln x from 1 to 3 minus a third of x squared. And I can totally integrate a third of x squared. It's just a polynomial, so I can do power up by 1 divided by new power. The third will still be there. Power goes up by 1, I divide by the new power. And now, if this was a definite integral, an indefinite integral, I would have stopped there and put a big plus c on the end. But since it's a definite integral, I will figure out what each of these things are. A third of 3 cubed ln 3 and a third of 1 cubed ln 1, and I'll subtract them. That's the first bracket, that's this one. And this one will be a third times a third of 3 cubed minus a third times a third of 1 cubed. Oh, so what have we got? 3 cubed divided by 3 would be 3 squared, which would be 9 ln 3. And ln 1 is 0. So that would just be 3. So it looks like I get 9 ln 3 minus 3 minus a ninth would be 2 and 8 ninths, or alternatively 27 ninths minus 1. Right. That's what that fraction works out to be. I think that's right. So 2 nights would be 18, and then plus another 8 would be 26. Yes, okay. Are you okay with what's going on there? You're just making sure you can see it, where everything came from?
Yeah,
Feel free to watch the video later so you can see it live. And I mean, I could figure out what that is, but you know, it's whatever it is. I could at least try and figure out if it's positive or negative. ln 3 is more than 1, so 9 ln 3 is more than 9. 26 over 9 is less than 3, so yeah, it's positive. It's a good start. In economics, you want to know whether things are positive or negative. It usually means whether it's a profit or a loss. And that's integration by parts. So any questions about integration before I turn off the video for this? Sorry? Thank you.